Hi, this is Mr. Ferris, and I thought I would walk you through a lesson just to be a little different. I feel kind of bad you haven't had any direct instruction, so I thought I would at least walk you through the normal distribution lesson guide, and we're going to take 2 days at this section. There's a lot of complexity in there, so we're just going to kind of walk through the first part of the lesson, and we will be going through this set of notes. Hopefully you downloaded that as a PDF off of Canvas. So let's start with the definition. And this is all in your book. You can always go back and do it yourself, but there's a few things I thought I would add that are maybe not exactly in your book. So a normal distribution, you've been studying different kinds of distribution, but this is a special kind that is a symmetric. Now, symmetric, of course, can be lots of different shapes. Symmetric can be high on both ends, low in the middle, that sort of thing. So we got to add some more descriptions to that. This is the one that really gets it nailed down. Bell-shaped. Of course, you got to know what a bell looks like. A bell is kind of like this. So that might be the only thing you really need. If you say a bell-shaped distribution, that's really what we're talking about. And but one more descriptor is it has a single peak. Boy, I am having trouble spelling already. Single, totally messed that up. It's amazing kind of the skills that just go away, like spelling, for instance. So a symmetric bell-shaped single-peaked distribution. That's the official definition of a normal distribution. Now, one of the features, I'll just put that up here, one of the features about the peak, if you can imagine having a number line on here, right in the middle, the peak will tell you where the mean is. Where the median is, they will be pretty much the exact same number. And that will be where the mode is. That's where the most common set of data is right in the middle. So you've really got a very specialized distribution. It's not just symmetric and bell-shaped and single peak, but that peak also represents all three of those. And then the variation is measured in standard deviations. We're going to talk a lot about standard deviations, which was a previous lesson. Hopefully you remember how to calculate that. So example one is just simply looking at two distributions of data and saying, are either of those what we would call a normal distribution? Well, if you look at the first one, I know this is a histogram, so it's kind of jaggedy, but if you can imagine, kind of making a shape out of it with a very smooth curve, looks like it fits all three criteria. It is symmetric, it's bell-shaped, and it has one peak. So I think we'd say a resounding yes for the first one. That's approximately normally distributed set of data. And when you think about it, these are chest circumferences of a bunch of Scottish men. And a lot of measurements kind of like this, where you're measuring something like height or weight or even finger length, foot length, that sort of thing. Typically, if the variation from what's typical is kind of random like or chance like, and you have some high and some low, but they're not that many, that's the kind of data that will tend to be a normal distribution. Now, population density, clearly, if you superimposed a curve on here, this is not. This is no. And the main reason is it's skewed right. Skewed right distributions are not symmetric. Those are incompatible with each other. So because it's skewed right, that cannot be a normal distribution. Your book also talks about 4 criteria, and 2 of which are just printed here, copied and pasted. So we're going to fill in 2 other ones. One of the features is that the data are clustered near the mean, near the middle. And so you've got a well-defined single peak right in the middle. Another condition is the data are spread out evenly around the mean. Evenly meaning about the same number on both sides, but with less probability as you go to the extremes. Larger deviations from the mean are rare. That's where you get those tails on both sides. And then the data result from many, and I'm going to add a word that's not in your book. I'm going to say that these factors are sort of random. Now, I don't know, they may not be like rolling a dice kind of random, but they're behaving like you would be rolling dice or flipping coins. I call those random factors in AP. And for instance, the chest circumference, most men have chests somewhere around 39 to 41. That's pretty typical, pretty average. But due to genetics, due to maybe nutrition, due to environmental things, you might have some men that are bigger chested and some that are smaller chested. Those are just things that happen sort of kind of randomly or by chance, and that's what accounts for the two tails on both sides. So those are the conditions that your book says will generate a distribution that is what we call relatively normal. And so if you think about scores on a really easy test, here's where we got to think a little bit. So imagine you've got, let's go 0 to 100%. If you're imagining a distribution of scores on a really easy test, well, if it's easy, I would imagine there's a fair amount of people that got perfect scores, and there's a lot of people that maybe got near perfect, and there should be a lot of scores up here in the top end. But then as you go down closer to 50% correct, apparently there's not as many people that got scores down there. And so what I hope you can imagine is that this is not going to be a symmetric distribution. There's going to be a ton of really high scores and not many low scores. So this would be skewed left. So we would say, no, this is probably not going to be a normal distribution because it's skewed left. You do have to kind of put the story together based on just some common sense things. Shoe sizes of a sample of adult women. Well, I've actually taken data from my students about their shoe size. And shoe sizes range roughly from 5 to 9 in the women's world. Now notice it says it's women. That's important. If it's women, most women have shoe sizes around 7. I think 7 is kind of the average. So you'd have a lot of 7s and 7.5s and 6.5s. But, due to genetic differences and due to environmental differences and whatever, you'll have fewer that are really have big feet and fewer that have really small feet. So I think we could kind of make an argument that, yeah, this is probably going to be normal-like. Most women are going to have shoe sizes around 7 or a little above and below, and not many really big, not many low. And that's what kind of generates a normally distributed distribution. Now, if this were people, like all adults, then it's not going to be normal because what likely you'll have are men who have feet that average maybe 8 and women who have average around 7 or something to do with their genders that would make that maybe have 2 peaks instead of 1 peak. So if this was adults, we might have to change our mind and say no. But if it's just women or if it's just men or just children, then maybe we could argue that it's approximately normally distributed. All right, on the back side, you have this nice diagram. And all of a sudden, we've switched from a normal distribution to a normal curve. The title of this part is a normal curve. So all of a sudden now, we're focusing on the beautiful, perfect mathematical curve that's generated and is put, maybe you could imagine this being put over on top of other data. In fact, I've got some data here from students in the past, and you see that these are the heights of a bunch of students, and you can kind of see that it's roughly, high in the middle. It's not quite as peaked as maybe you might imagine, but it still has very few on both ends, and it's most of them are kind of in the middle. And if you just took one of these beautiful mathematical curves and just sort of superimposed it on top of the data, you would see that that curve, which is a mathematical thing, it's coming from a formula, fits sort of kind of the rough data approximately well. And so the thing that we can jump to then, if data tends to pile up like this curve being mathematical allows us to use shortcuts and calculus, basically buttons on our calculator that'll get these answers very quickly. I believe your book is going to use a table, not a calculator. But the idea is that there are certain properties of the curve, the mathematical curve, that we can kind of use as an estimator for what's going on in the rough data. For instance, according to your book, you will find that roughly 68% of all data sets that are normal are going to be within one standard deviation of the middle. So if you were able to start in the middle and go out one standard deviation on both sides, you would find that about 68% of the data is going to lie in there. Now, if you go out two standard deviations on both sides, you'll notice that roughly 95% of the data is in there. And if you go back to my data set, I actually told the computer to calculate it. And notice what the calculator came up with. If you go out one standard deviation, look at that. It's about 0.65 or 0.66. So that's roughly, 68 is what they say. But we got 66. That's pretty close. And then two standard deviations is supposed to be 95 according to the rule. And we got 97. So if you would actually count the dots, you can see that this is just a rough rule of thumb. It's not a perfect rule, but it gets you close enough. So this idea of 68, 95, and then if you go out 3, basically, you could just call that 100%. Usually with most data sets, you go out 3 standard deviations and everything is in there, typically. So to summarize, about 68% of the data, we can finish this off and say something like fall within one standard deviation of the mean. When you go out 2 standard deviations, it's about 95%. I guess I can do all that. And then when you go out there should be a 99.7 there. About 99.7% of the data fall within 3 standard deviations of the mean. So there's your rule that is just a kind of a rough estimate rule. It's a rule of thumb. But we can use it to make some good general guesses about things. Like, for instance, here's a vending machine that if you make one of these distributions kind of by hand, you can just do a little quick sketch. It's not that hard. It says that the mean is 5.67, so we can put that right here. And then if you go out 1, 2, 3 standard deviations and 1, 2, 3 standard deviations, that third one should be pretty much at the end of the visible part of the curve. And then it says the standard deviation is like 0.07. So if you add 0.07, you'll get 5.74, you'll get 5.81, and you'll get 5.88. If you go down on the other end, I'm just going to skip to the one that's important, the 5.53, because the question they ask is, they want to know if the vending machine is adjusted to reject quarters that weigh more than 5.81, that would be out here, or less than 5.53, that would be out here. They want to know what percent of coins are going to be rejected in those two areas. So what we have to do is we've got to figure out exactly how much would be out in that top range. So where are we exactly? Well, we are 1, 2 standard deviations on this side and 1, 2 standard deviations on this side. And so you might remember our rule. When you go out 1, 2 on both sides, then we have about 95% of the data in the middle. So on the outside, if this is symmetric, you'll have about 2.5% above the second standard deviation and about 2.5% below the second standard deviation. And so altogether, you'll have about 5%. About 5% of the quarters will be outside of 2 standard deviations. So we can use this 95% rule to even just do a rough estimate without even using a calculator, honestly. You're just kind of doing it in your head. And one final question. This is going to be kind of what your homework is going to be on and your first quiz. So if we do another normal distribution, this time the average is 78, so we stick 78 in the middle. And if we go out, I think what they're wanting is just to write some questions. So if you can imagine going out 3 standard deviations on both sides, and we can just subtract 4, and subtract 4 to get the numbers for those 3 marks. Above 78, if we go a standard deviation of 4 above 78, that would be 82, and then 86, and then 90. So what we've done is we've labeled this with kind of the 6 standard deviations. And they want us to write 3 questions. If this was a test, and this was the average test score, what kind of questions might you write to have somebody solve? So I was going to suggest maybe, maybe a teacher says, I'm going to make an A anybody that gets 86 or higher. So what percent, we could write a question that says what percent gets an A if an A has to be greater than 86. Well, if we think about this, remember last time we said 95% is in the middle, 2 standard deviations. This is 2 standard deviations above average. So we already said that this little tail is 2.5%. So the answer to that would have been 2.5%. So this would be, I suppose, kind of maybe a little difficult test when only 2.5% of students get an A. Or maybe another question might be if passing is greater than, let's say, 74, what percent passed? So greater than 74. 74 is right there. And remember, we know that if you go out 1 standard deviation on both sides, according to this little rule of thumb, there should be 68% in the middle. Well, if this is perfectly symmetric and there's 68% in the middle, subtracting from 100% gives us 32%. And if you divide 32% in half, then each half is going to be, half of 32 would be 16%, wouldn't it? So it looks like if the passing, you have to get 74 to pass, 16% are going to fail, and then I guess that'd be 84% would be on the other end, which is all the rest of this would be a passing score. So I could say that 84% are going to pass the test because I know that 16% are going to fail. A lot of times you can get an answer by subtracting from 100%. So those might be a couple questions you could ask about a distribution where you know the mean and the standard deviation and you know it's normal. So your homework is going to be page 393, problems 15, 17, 19, and 21. I think this will be on Canvas too, but I thought I'd write it down here. Those are your 4 practice problems, and many of them are just very similar to the ones we just did here. So good luck with that. As always, if you have any questions, by all means, send me an email, and I'll do my best to answer them. Have a good day and week.